In the previous class, we started with the concept of trees, guys, right? So, what is the general meaning of a tree? A tree is a collection of data items where one node will act as a root node and the remaining node will act as child node sometimes, sometimes will act as a leaf node, sometimes will act as a parent node, sometimes we can call it as intermediate nodes also, right? Basically, if you are going to classify it, trees will be comes under non-linear data structures, right? So during the starting classes, I have classified clearly arrays, linked list will becomes under linear data structures, where a node can have only two elements. One is prefix element, another one is a suffix element. We call it as linear data structures. If a node having more than one suffix element, it will becomes under non-linear structure. And the main reason why we are moving for trees is used for to represent hierarchical data. If you remember the earlier class clearly, which is meant for to represent the hierarchical data, we are moving for trees. I mean, in general, if you go with the concept of arrays, or if you go with the concept of linked list, we are going to represent the data in the form of what? In a straight line. Am I right? The data will be represented in the form of simple straight line, right? If we are going to store the data in the form of a simple straight line, for example, I would like to apply some kind of operations, like some kind of searching operation. If I am going to apply searching operation over the arrays, like let's say arrays can be of two types again: unsorted array, sorted array. In unsorted array, searching will take what is time complexity? Big O of n, obviously. In sorted array, what will be the time complexity? Big O of log n. Good. But if I am going to implement the same searching concept on the straight line format data using linked list concept, whether it might be unsorted linked list or it might be a sorted linked list, what will the time complexity? Big O of n. Why big O of n? Random access is not possible, right? In linked list, random access is not possible. Because of it, we are going to get a time complexity of big O of n, right? Suppose in arrays, if you have a sorted data, you will get the better performance. Okay. But if you are going to observe the linked list, even the data is in sorted order. I mean, if I am going to write clearly, it might be either in unsorted or it might be a sorted. It is going to get a time complexity of big O of n. So the question here is, do we have any solution? Which will take lesser than big O of time complexity for searching operation? The simple answer is trees, right? That representation is hierarchical data, right? This is all what we discussed in the previous classes. If you are going to represent the data in hierarchical order, instead of representing in a straight line, you can get definitely time complexity of lesser than big O of n. Based on that, we have discussed various kind of trees: general trees, binary trees, okay, complete binary tree, tertiary tree, right, expression tree, various kind of things we discussed, right? Among those, we have majorly concentrated on one type of tree, which is binary trees. What is the meaning of binary tree? Binary tree means if you take a node, a node can have 0 or 1 or 2 children, right? In other words, as per your statement, we can say it as it's having at most 2 children. If a node having at most 2 children, we can call it as binary trees, right? Based on again the number of children, we can classify it as again full binary tree, perfect binary tree, complete binary tree. All those things we have discussed. Fine. Now in this session, we will try to concentrate on how to implement these binary trees. Implementation part. I am going to give the implementation part, right? Basically, if you wish to implement any kind of concept, it might be any kind of data structure, internally you are going to use arrays and linked list, guys. Am I right? If you are using, either it might be a kind of queues, stacks, or it might be any other kind of data structure, internally definitely you are going to use the concepts of arrays and the linked list. For example, there is a binary tree. Something like this: 1, 2, 3, 4, 5, and let's say 7. Or else I wish to continue further, 8, 9. Okay, so this is the general binary tree as per our knowledge, right? The same thing will be reflected in the system directly, or I mean, is the same image is going to be stored directly, or it will store in the form of some other representation. Something like arrays and the linked list. It won't show the image directly, right? So if you observe the linked list, how we will be able to represent? If I have a node 1, this node 1 is connected to the node 2 and node 3, right? So which means a node should be connected to two nodes. Then can I consider some kind of double linked list node? If you observe something like this, the node 1, this is node 1, where the middle part is the data part, left part is the pointer connected to the left child, right part is the pointer connected to the right child, right? Observe it. This is the node 2 and node 3, and you know, once the memory is created, it's having some address like 100, 200, 300. So node 1 wants to connect to its left child, it has to have which address? 200. If it wants to connect it to the right child, it has to have the address 300, right? So similarly, you can move on implementing it. So 4, 5, so it will be connected something like this. Okay. So similarly for here, 8, and this will be 7, and for 8 the left side will be. If you observe clearly, for every node we have an address. So let me say 400, 500, 600, 700, and this will be the 800. For 2 left side, you should be connected to which one? 400. For 2 right side, should be connected to 500. For 4 left side, null. It should be null. Means there are no left children, there are no right child. For 5, left side will be null and right side will be null. For 8, left side will be 800, right side will be null. This will be null, and null. Which means, if I have a question, does node number 3 is having left child? Yes or no? Yes, right? So can you answer what is the child of 3? So I can say, what is the left child of 3? 8. You can able to easily answer, right? Which means that you will just take the left pointer address. If it's having an address, you can definitely move to the left location, you will get its data. So this is the way you can able to represent the general tree in the system. Okay, fine. The same concept, how to represent in arrays. In arrays, you will have a complete an array. You know, it starts with addresses, indexes like 0, 1, 2, 3, and so on. Fine. Then how the arrays will store the data? The arrays will store the data in the form of level by level, guys. It will store the data in the form of level by level. So this is what we can call it as level 0. In the last class we discussed something like level represents the distance from root node to the respective location. Root node to root node itself is 0. Level 0. Next one is level 1, level 2, and so on. This is level 1, level 2, and so on. So we'll try to store it in level by level. So first, in the level 0 we have 1, 2, 3, 4, 5, 8, 7. So level 2 completed. In level 3, what are the elements are there? Only 9 is there. But can I store the 9 directly here? In general, if you are interested, you can store it, but you can't able to use it further. There is no specific meaning for it saving like that. So instead of it, what you can do now, try to assume that there are certain elements are there for the left child of 4 and the right child of 4 and left child of 5 and right child of 5, then store the 9, which means that, can I say something like this? This is empty and this will be an empty and something like this, 9, 10, 11th index position. So this is here 9. Have you observed what I am doing here? We'll move on the process. We'll continue the process. So why I am mentioning like that means there is some advantage if I wish to continue. So I have specifically given some blanks because there are no elements here. Okay. Now the question is, if you are going to represent the array something like this, and assume that you won't have this structure, can you able to answer what is the left child of 3? Assume that you are not having this particular image, and this is the array only you have. This is the only array you have. Can you answer my question? What is the left child of 3? No? Observe. So can you find out some relation? 3 left child is what? 8. Okay. And what is the left child of 2? Good. What is the left child of 8? 9. Left child of 8 is 9. Assume, okay, now answer. What is the right child of 3? So I am trying to point out to the respective location. Right child of 3 is 7. What is the right child of 2? Right child of 2 is 5. Right? So now based on these indications, can you able to observe some relation? Try to figure out some expression with respect to its indexes. Observe, if I want to find out the left child of 3, if you want to find out the left child of 3, 3 left child is available at which location? 8. What is the index position of 3? 2. What is the index position of 8? 5. Can you able to figure out 2 and 5 relation? So, I mean, you have to make it analyze it. So then, if you want to find out left child of a particular node I, you can able to get it with 2i plus 1. 2i plus 1. Observe, the index position here is 2. 2 into 2 plus 1, which is 5. Fifth index position, you have the left child 8 or not. Similarly, observe, apply the formula for the index position 1. What is the left child of 2? 2 into 1 plus 1, 3. Go to the index position 3 and you have you got the 4 or not? Yes, right. This is how system is able to find out the left child and the right child. So here I am assuming that index position is what? Index position starts with 0. Index position starts at 0. Right? Based on this assumption, you got the left child as 2i plus 1. What about for right child? Right child of ith index position element, 2i plus 2. That's it. Okay. Suppose for example, if you are able to generalize it, if the index position starts with 1, the left child, can you able to generalize it, which is 2i, and the right child of ith index position element is 2i plus 1. So this is what you have to observe with this particular arrays representation. I mean, in general, you can able to represent our imaginary data, which is represented in a hierarchical manner. You can able to store it in two variety of ways. One is arrays representation, another one is the linked representation. Once you are able to store in arrays representation, if somebody asks what is the left child of particular node, you have to have a question like what is the starting index position. If it starts with 0, the left side will be 2i plus 1. If it starts with 1, the left side will be 2i, and it has to work accordingly. Right? These are the two different ways you can able to store the data. Right. So once you are able to understand how to represent the data, then we can able to perform traversing over it. So we call it as traversing techniques. You can call it as tree traversing techniques. Right? For example, let me have some structure, something like this: 1, 2, 3, 4, and 5, and assume that I have 6 also there. This is our imaginary binary tree. Is it a binary tree? Yes or no? Yes, it is a binary tree. The same binary tree, can I able to construct using linked list representation? Yes or no? So I will try to construct it using linked list representation. I have node 1. Node 1 is connected to node 2. Node 2 right child will be 4. Right child will be 4. And for 1, the right child will be 3. For 3, left child will be 5. For 5, right child will be 6. Right? I think this is the structure you have to. Okay. So based on this, I will try to draw the expressions 100, 200, 300, 400, 500, and 600. So what about the left child of 1? 200, right child will be 300, and this will be null. Here it will be 400. Left side is null, right side is null, and here it is 500. This one will be null. Left side is null, right side is 600, and here the both sides are null. This is a linked list representation of a binary tree. Okay. So once you have a tree, in general, if you have a linked list, normal data, how we are going to traverse, how we are going to find the searching, how we are going to find, or how we are going to perform searching. In general, in linked list or in array, how we are going to perform searching. If data is in sorted order, we can apply binary search algorithm. If data is in unsorted order, we will try to perform linear searching fashion. Similarly, on trees means what? The data is represented in the form of some hierarchical order. How we are going to find searching? By applying traversing technique mechanism. Right? So if you want to perform any operation, insertion, deletion, or search, whatever the operation you want to perform on hierarchical representation, we can go for first, what you have to do? You have to identify in which location you have to add the data. If you want to identify in which location you have to add the data, first you have to know various kind of traversing technique mechanisms. So there are 3 types of traversing technique mechanisms are there. One will be pre-order traversing technique. Another one is in-order traversing technique. Third one is the post-order traversing technique. So these are the 3 different ways we can able to perform traversing over the RM, over the linked list. Okay. Sir, what is the meaning of pre-order traversing technique? So pre-order traversing technique means while searching data, what you are going to do? You will try to follow the pre-order mechanism. Pre-order. Pre means what? First we have to perform some operation, then you have to go for further process. What does that means? Whenever you wish to perform pre-order traversing mechanism, first you are going to print the data. First you are going to apply the mechanism. Do you wish to perform searching or not? If you wish to perform searching, apply the logic searching. Then you go for visit the left childs. Then visit the right childs. Have you understood what I am saying? For example, let me try to write a small logic here. Void pre-order mechanism I am trying to perform, and I am having some node structure I am going to get. Okay, and if I say something, whenever I am going to reach, so I am just writing some dummy logic. If the node contains the value as null, what does the meaning of this one? We can simply stop the process. We can simply stop the process. I mean, I can say that that is the end of the node, right? So I can simply perform printf, let's say node arrow data, node arrow data. Instead of writing like this, to make it more generalized, I will simply stop the process. Am I right? Whenever you have a node as null, I will simply stop the process. Otherwise, I will try to perform something like this. Printf, let me say node arrow data. That's the meaning of print. Once we perform the print operation, then what you are doing? We will try to move to the left side. So to try to move to the left side, I will go for calling the logic pre-order of node arrow left. Once I complete the left side, what I will do? I will try to move for pre-order of node arrow right side. So now I hope you got the clear idea. Here the pre-order is a kind of a technique which represents, it's a kind of recursive mechanism to complete the traversing process of entire linked list structure. Generally, if you are not having any kind of tree traversing mechanism, then what you will do? There is no strict rules, then you will try to traverse in different ways. You might miss a particular path. Am I right or not? You might miss a particular path. Instead of missing different kind of paths, they have specifically mentioned certain rules. What are those rules? If it is a pre-order, first visit the data, then go for left. In the left, what you have to do first? Again print, and then I have to do the process, right? In order, what you have to do? Na? You have to first go for visiting the complete left, then you have to go for print, then you go for right. In post order means what? After completing all the process. I mean, after visiting the left node, after visiting the right node, then you have to go for printing. See, this logic resembles here. Okay. Now try to apply this logic. So, can you tell me here the in order logic? Void in order struct node star if node double is equal to null. What we can say? We can simply return the control to the calling function. If it is not this case, we will try to perform what first? We will move to the left side in order of node arrow left printf node arrow data, then go for in order of node arrow right. See, this particular logic, if you are able to clearly understood, it's a kind of recursive mechanism. Once I move to the left, again it has to start executing from starting onwards. Right? Similarly for post order, void post order of struct node star. Again, if the node contains a null, I can simply return it to the calling function. Return. So first, what you have to do here? You have to go for moving to the left. Node arrow left. Once the left completes, we'll go for post add node arrow right. Then once it completes all the data, then I will go for printing its data. So this is the logic behind these three traversing mechanisms, right? Once you understood this code, let me try to give you a simple example so that you will get clear idea. For example, we have a tree something like this: 1, 2, 3. Let's say 4 is the right child of 2 and 5 is the left child of 3 and 6 is the right child of 5. Now I wish to apply pre-order mechanism. Pre-order mechanism. In pre-order mechanism, what is our logic? First we'll visit the node. First we'll visit the node. Visit the node means what? I am trying to write it as print. Then I will go for left. Then I will go for right child. So what is the meaning of it is, observe it. Nobody asks the code in the examination. If it is a kind of complex examination, they will try to ask for what is the output of the pre-order traversing for the given tree. That's it. Right? You have to know how to traverse it. So in general, in a linked list, you will be always pointed to the first node, root node, because once you point to the root node, you can able to traverse to any location, So in pre-order, is it a null or not null? Not null. If it is not null, what it will do? It will go for printing it. Printf node arrow data. What is the data you are going to get? Observe it clear. 1. Then it will move to which location? Pre-order of node arrow left. What is node arrow left? Which means it will move to the left side location. Is it null? No. Then it will execute which statement? Node arrow data. Node arrow data. So here you will get the data something like 2. Okay. Then it will go for again calling node arrow left. Is there any left is there? No. Empty. When the left is null, it will simply given the control to the back. So at the node number 2, what are the steps completed? Printing done, left is done. So I will go for right side part. In the right side part, is it going to be first what? Print. Then go for left side. Nothing is there. Right side. Nothing is there. Getting. So 1, 2, 4 done. Then it coming back. Now 3 will be printed. Okay. Then left side part 5 will be printed. Left side nothing. So move for right side. Right side part first print. Then left side part nothing. Right side part nothing. So getting back. And then right side nothing. Getting back. Right. As you reach to the final position, this is the output for the pre-order traversing technique. For the given tree, it is the output. Right. Basically, this pre-order traversing technique use it to calculate prefix expressions. Okay. So if you observe clearly, I have the data something like this, right? 1, 2, 3, 4, 5, and the right side is 6. Observe it more clearly. I started with 1. Just try to draw the pen, right? You are at this point, right? Whenever you are visiting for the first time, try to note down its answer. Right? I am trying to explain it for the gate level. Whenever you are visiting for the first time, try to write the answer. So as I am visiting for the first time, 1 is the written in the output side, and I am visiting. Is it for the first time or second time? First time. So write down. Visit. So left side nothing. So whenever I am getting back, this is what time? Second time. So don't go for writing. So something. Is it for first time? Yes. Left side nothing. Right side nothing. Moving back. Okay. This is second time. Again first time. Right? First time. So here it should be left side nothing. So right side first time, second time nothing. So you should not worry about the second time and third time visit. You have to only consider about the first time. So if you are trying to note down the visiting the nodes for first time, you will get definitely the output as pre-order traversing technique. Okay, fine. Next, let me try to take out the same diagram and try to apply in-order traversing. Suppose for example, if the data is something like this, 1, 2, 3, 4, 5 and 6. Let me apply in-order traversing. In in-order traversing, what will the logic? You have to go for left, then printing data, then we'll go for right check. So we'll try to start from the root node. So in the root node, what you are going to do here? We'll apply first left. We'll go for left. And you are at the number 2. Will you print it or you will go for left again? We'll go for left. This is a recursive process. Once you call it, you are trying to call the in-order process continuously until what? Left, left, left. Okay. So you should not directly print it. You have to go for left. You will come back left. Is there any data is there in the left? No. Then cursor will come back and you will try to perform print operation. Printing means what here? 2 will be printed. Then the right side. In the right side, will you print or will you go for left again? You have to go for left. Always try to think about the left side part. Left side, nothing. So 2, 4 will be printed. Next right side, nothing. So then coming back. Okay. Then 1. Observe. Now 1 should be printed or not? 1 should be printed. When the 1 will be printed? Once the left side part is completely printed, then we'll go for printing 1. For 1, left child is completed, then only the 1 will be printed. Okay, na? So this is the logic you have to observe. Then go for right side. In the right side, again you have to go for left side. Left side 5, you have to go for nothing. Then you have to go for printing 5. Printing 5. Then in the right side, you have to go for 6. For 6, first you have to complete the left side. Then you have to get 6. Right side, nothing, getting back. Getting back. So 5, left side is done. I mean for 3, does the left side is complete or not? Yes. Then you go for printing the 3. So right side done, getting back. That's it. So this is the output you are going to get once you visited in-order traversing technique. Observe in this scenario, if you have the same structure, 1, 2, 3, 4, 5 and 6. In this scenario, the simple logic is, whenever you are visiting for the second time, whenever you are visiting for the same node second time, then you write in the output. So before that, let me write, generally the in-order technique used at binary search tree sum. That we'll see in further classes. We will basically use at binary search trees to get sorted data. To get sorted data, we will use the in-order traversing technique. Fine, observe. Now apply the logic. You are at 1. Is it for the first time? Yes or no? Okay. So I am moving. Is it for the first time? Yes. Left child is there? Nothing. So now observe. Is it second time or not? Whenever I am visiting for the second time, try to write the output. Now moving. Is it for the first time? Yes. Left child nothing. Is it for the second time? Yes. So is it now third time or not? Right child is nothing. So getting back. Is it third time? Yes. So getting back. So second is how many times we did so far? 2 times. This is third time now. So now observe. Now 1. We are at 1. Which is at second time or third time? Second time. Okay. First time. First time. Nothing. Second time. First time. Second time. Third time. Third time. Second time. Good. And then third time. This is third time. This is third time. Right. So once you done this one, is it completed or not? Right. This is the order you are going to get once you apply the in-order traversing technique. Okay. Fine. Similarly, if I am able to apply the post order for the same data, if I have the same tree structure, and for post order, what is the logic you are going to follow? You will try to print the data at the end of completing both left child and the right child. So left child should be completed, right child should be completed, then only you will perform print operation. Observe it. I am at the node 1. I am at the node 1. So far, have I completed the both left and right childs? No. So I will go for first completing the left side. I am at 2. Have I completed the both left and right child? No. I will go for left part. Is there anything is there? No. So I will go for right side. In the right side, at 4, do I have completed both left and right? No. So I will go for left, nothing. I will go for right side, nothing. Now at 4, do I have completed both left and right? Yes. So I will try to put it in the output. Right? Then I will move back. At 2, do I have completed both left and right? Yes. Then I will go for printing it. Now at 1, do I have completed both left and right? No. We have completed only the left part. So I have to go for right side part. So based on that, you can go for it. At 5, left side is done. What about right side? Not yet done. At 6, left side done, right side done. So we'll go for printing 6. At 5, both sides done. At 3, right side not done, so completed. So it will be done 3. Then finally you will get, this is the post order traversal for the given tree. If you observe the same structure by applying post order, what you observed then? What you observed? If you go for the pre-order, so when you are going to perform the operation, whenever you are going to visit for the first time, whenever you are visit for the first time, you can get the data. For the in order, when you visit for the second time, based on that, for post order, whenever you are visit for the third time, you can get it. You can get it. Okay. So observe, I am at the node 1. It is first time. This is first time. Left side nothing. Second time. Fourth is the first time. Left side nothing. Okay. Second time. Right side nothing. Now third time. Right. Whenever you are visiting for third time, 4. Now second one is how many times we did? Third time. 2 done. Next node 1. Second time. Node 3, first time. Okay. Node 5, first time. Second time. Node 6, first time. Left side nothing. Second time. Right side nothing. Third time. 6. Node 5, third time. Very good. Node 3, second time. Right side nothing. Third time. Next, this is for third time. So this is the data you are going to get when you are working with the post order traversing technique. Is it clear for everyone? So what you will do now? Try to apply the mechanism for the other question. If the data is something like this: A, B, C, D, E, F, G, H, I. Apply pre-order technique, in order, and the post order technique. Solve it, ma. So in the examination, you have to write the step-by-step process. You should not go for shortcut process. If it is a multiple choice question, you can go for your own procedure to get the output. But in the examination, you have to write step by step. వచ్చినప్పుడు చెప్పండి. Okay, Mike. Have you completed? Right. Observe. In pre-order, the logic is print, left, right. Right. In order, left, print, right. In post order, left, right, and then we go for print. Okay, so I am going to use just shortcut. Observe it. I am trying to visit for the first time, right? So for pre-order I am trying to write A, B, D, E, F. Okay, then getting back all the things C, G, H, I. Pre-order is very easy, right? I will just completely traversing for the first time. I will try to go for in order. In order, start with A, B, D, left side is done, so second time. D, E, F, second time, so you will get F will be printed. E is the second time, B, second time done, A is the second time. Okay, C, G, second time, G, I, H is the second time, C second time. That's it. Is it? Have you got the same answer for everyone? Okay, good. Next, similarly for post order. For post order, start with A, first time, second time, first time, second time, third time. F, second time, third time, E, third time, D, B, third time, A, second time, third time, H is the third time, G, third time, C now third time, then go for E, right? If you got this answer, then it is correct. Right? This is how you can able to find out the pre-order, in-order and post-order mechanisms when you get any kind of tree as input. Okay, fine. So once you get the idea about how to perform traversing over the trees, then the question is, can we able to construct a tree from given traversal mechanisms? I mean, if you observe here, they have given the inputs, let's say pre-order, in-order and the post-order. If you have given with the pre-order, can you able to construct back the tree? For example, let's say you have the data, something like let's say post order. The data is something like 4, 9, 8, 5, 2, 6, 11, 10, 7, 3, 1. Can you construct a tree by just looking at the post order? Can we construct a tree just by looking at the post order? Is it possible? What is the logic behind the post order? Left, right, head, print. So, okay, fine. Which we can say it as print. Good. Right. Once we know this logic, can we able to construct back the tree? right? If you are able to clearly observe it, print is available at the last option, right? So I can say that 1 is the root node, definitely. 1 is the root node because the last complete node in the post order is what? Root node, definitely. So you can observe it. But the question is, the remaining elements will definitely split into two parts. So they might fall in the left side or they might fall in the right side. But do you have the exact idea where it will fall? Do you have an exact idea where it will fall? No. So with the help of single post order traversal, you cannot able to construct back the tree, right? Which means by just simply looking at independent traversal techniques, by just simply looking at independent traversing techniques, can we able to construct back the tree? By just looking at the independent traversing techniques, can we construct a tree? Is it possible to construct the tree? Answer is no. It is not possible to construct because we can't decide which element will be placed on the left side, which element should be placed on the right side. See, you can observe for even in order also or even for pre-order also. You cannot able to construct the tree. Then, is it possible to construct with the help of combination of two? Let's say I am taking the same post order technique with the values 4, 9, 8, 5, 2, 6, 11, 10, 7, 3, 1. And I am trying to take the in order. In order 4, 2, 5, 9, 8, 1, 6, 3, 10, 11, 7. Can you able to do it? Answer is yes, it is possible. With the help of a combination of post order and in order, it is possible for us to construct the tree. How, sir? You can observe in post order the logic is you are going to simply following left, right, and I am saying that head means okay. Let's say print, which means the root element is definitely placed on which side? Last one. And what is the logic for in order? Left, print, right. Left, print, right? So, in post order, you already observed that 1 is the root element. 1 is the root element. With the help of in order, where the 1 is available? It's somewhere. It's not exactly, it's somewhere, right? Once you observe, with the help of in order, can you able to guess something? Where will be these elements will be available? Left side of 1. Where these elements will be placed? Right side of 1. So, now with the help of two combination like post order and in order or pre-order and in order, you can able to definitely classify it into which elements will be placed on the left side, which elements will be placed on the right side. Right? Observe it. Now I will try to construct the tree. In the first step, we got the complete idea. 1 will be placed here, right? And then on the left side part, what elements will be there? 4, 2, 5, 9, 8. And on the right side part, 6, 3, 10, 11, 7. Good. Fine. Now the question is, among 4 to 5, 9, 8, among 4 to 5, 9, 8, which one will be the root node? Among the 4 to 5, 9, observe here in the post order, those will be available at certain location. 2, right? Good. So if I say left, right and print, 2 will be the root node. Why 2 will be the root node? As per the logic of post order, the last node will be acting as a root node. So which means among this entire data, 2 will be the root node. 2 will be the root node. If 2 will be the root node, out of all these elements, which elements will be placed on the left side? Observe in the in order. In the in order, you have to apply 2 left side will be 4, 2 right side elements will be 5, 9, 8. Among this 5, 9, 8, which elements will be again on the root? Again go for here. Which is the root? 5 is the root. When 5 is the root, which elements will be on the left side, which element will be on the right side? This 5 is the root. Only right side. There are no left side element. So I'll go to the right side and I'll place 9, 8. Right? Again in 9, 8, which one is the root? 8 is the root. If 8 is the root, which is the left? So this is how we can able to construct. So left side is done. Similarly, go for right side part. 6, 3, 10, 11, 7. Which is the root? 3 is the root. If 3 is the root, 6 is the left side. As there is only one element, we can directly place it. And the right side part, 10, 11, 7. Out of 10, 11, 7, which one is the root? Can I write directly? 10, 11, 7. If you remove it, 7 will be the root. If 7 is the root, which elements on the left, which elements on the right side? 10, 11 are the left. Right? Out of 10, 11, which is the root? 10 is the root. Right? And for this right side will be 11. So the final answer will be 1, 3, 4, 5, 8, 9, 7, 10, 11. So we can able to construct back an inequity tree. We can able to construct the inequity tree with the help of the combination post order and the in order. Similarly, can you able to construct a tree with the help of, let me give you in order or pre-order first. Pre-order 5, 3, 1, 2, 4, 6, 8, 7 and an in order 1, 2, 3, 4, 5, 6, 7 and 8. Okay, can you able to construct back it? Right, as it is possible. With the help of a combination, we can able to exactly classify the data. So this combination is possible. Right? Observe in pre-order, the logic is what? First, print, left, right. Here left, print, right. So first element itself is what? 5, root node. So I am trying to construct it 5. So the left side will be what? 1, 2, 3, 4. Right side will be 6, 7, 8. Right side will be 6, 7, 8. So I will try to write something like this. 1, 2, 3, 4. Right side will be 6, 7, 8. Out of this 1, 2, 3, 4, which is the root node? 3 is the root node. If 3 is the root node, what should be the elements on the left side? 1, 2. What should be elements on the right side? 4. So can I write 4 on the right side? As we have only one element, I can write it right. Out of 1, 2, which is the root? 1 is the root. If 1 is the root, right side will be 2. Right side will be 2. Okay. Next, with respect to 6, 7, 8, we have to do 6 is the root node. If 6 is the root node, 7 and 8 are going to be placed on the right side. Right? Again 7 and 8, you have to go for 8 is the root node and 7 is the root. So this is how you can able to build that tree. Okay, fine. Now we left with one more combination. We are having 3 possibilities, right? Pre and in, post and in, pre and post. If you have the data something like this, if you have the data something like pre and post order, can we able to construct that tree? Can we able to construct that tree or not? The answer is yes, we can able to construct that tree. Okay, but we cannot able to construct. We cannot able to construct what tree? Unique tree. With the help of combination of pre and in order or post order and in order, you will able to get only unique solution. But if you go with the combination pre and post, it is not possible for us to construct the unique tree. Why? What will be the reason? Observe in post order, let's say, we'll go with this slide. In pre-order, you are saying that A is the first node. In post order, you know A is the root node only. In pre-order, you know A is the root node. In post-order, you know A is the root node. But at any one of the traversing technique, have you got the clarity which elements are fall on the left side, which elements are fall on the right side? No, it is not possible, right? Because this is a continuous sequence data. This is a continuous sequence data. That's the reason you can't able to construct the unique tree. But if you are able to try with different number of times, finally you will get the solution. But it might not be the unique solution. So that's the reason this combination is going to be avoided. Okay. So now try to construct the unique tree for the given data. For example, the in order they have given as DBH E I A F J C G, and the post order is DHI E B J F G. Better you can change the question, right? You might get the questions in the alphabetical order also. You should not get confused. Okay. So let me give some numbering in order. The in order is 1, 2, 3, 4, 5, 6, 7, 8, and the post order is 2, 1, 4, 3, 7, 8, 6, 5. Okay, this is one question you can solve, and the another question in order DBEA FCG pre-order ABD ECFG. Solve these two. Do you need the earlier slide? So you can prefer the second one. Second diagram prefer change. In the exam you have to write the solution, right? You can prefer the second one. So have you completed ma? అందరూ కంప్లీట్ చేశారా? వెరీ గుడ్. సో అబ్జర్వ్, if you are trying to solve the given order with in order and the post order. So in post order, you know the root node is what? The last element. If 5 is the root node, what elements are going to be placed in the left side part? 1, 2, 3, 4, and right side part will be 6, 7, 8. Among the left side part of 1, 2, 3, 4, which should be the root node? 3 is the root node. If 3 is the root node, what elements are going to place on the left side? 1, 2. What elements are going to place on the right side? 4. I can directly write it. Among 1, 2, which is the root? 1 is the root node. If 1 is the root node, right side will be 2. Okay? Fine. Similarly for 6, 7, 8, which is the root? 6, 7, 8, which is the root? 6 is the root node. Then, is there any left side are there? No. Complete right side. Out of 7, 8, which is the root node? 8 is the root node. And then left side is 7. So this is the final diagram you are going to get when you are working with this combination, in order and the post order. Is it the same for everyone? Very good. Similarly, if you have the combination in order and the pre-order, what you have to do? Pre-order, in pre-order, A is the first one. A is the first one. If A is the root node, the DBA will be comes under which side? Left side, and FCZ will be on the right side. Right? In DBE, which is the root node? B is the root node. Very good. B is the root node. If B is the root node, D will be on the left side and the right side. Right? As we have only one element, so we can directly write it. So this will be D and E. And if you go for FCZ, FCZ, what is the root node? C is the root node. Then left side will be F and right side will be G. How I decided? This is the C. C left side is F, C right side is G. So this is how we can able to construct the tree. Is it clear for everyone? Fine. So this is the way you can able to construct the trees. Fine. So observe clearly. We started discussion on tree sum. Am I right? We started discussion on trees. Then we have seen how to implement the binary trees. How to implement binary trees. Then we have seen how to perform traversing on binary trees. Once you know how to traverse on binary trees, we can able to construct back binary trees. We can able to construct binary trees. These are the things that we have seen so far. Fine. So there is some other version of binary trees are there, which we can say as heap trees. Heap trees. Sir, what is the reason why you are moving for heap trees is, there are, for any kind of data structure, there are specific advantages are there. For example, if you have some unsorted array, in an unsorted array, trying to insert an element, how much time complexity is going to take? In unsorted array, what is the time complexity to insert the data? Big O of, do we need to perform any comparison? We'll get the data, we'll directly place it, right? So it will, we can say it as big O of 1. Unsorted, we are just simply placing it, right? Why are we having question again? What about for deletion? We have to first find the element. The element might not be available, so it is going to be big O of n. For search operation, big O of n. Okay. Similarly for sorted array, for insertion, how much time complexity is going to take? Is it 1 or n? N, because we have to place it at exact position. We have to place it at the worst case, you might have to shift n elements. So it will be big O of n. Similarly for deletion, big O of n. For search operation, log n. You should not get confused. Searching is different, deletion is different. In deletion, you are going to first perform search, then delete. While deleting, you might have to shift n elements to the left side. Then you have to require n iterations. So for deletion it is big O of n, for searching it is big O of log n. Observe clearly here, for the insertion operation in unsorted array, it is performing best case, okay, big O of 1. Okay, good. But what about the deletion operation in unsorted array? Or what about the deletion operation in the sorted array? What about the insertion operation on the sorted array? Is it behaving some worst case or not? It is going to take a time complexity of big O of n. Big O of n. Now the question is there any solution? Is there any solution which will get a time complexity of lesser than big O of n? Lesser than big O of n. Then the concept they have introduced is heap trees. Heap trees. In heap trees, for insertion and deletion, it is going to take a time complexity of big O of log n, not big O of n. This is the main advantage of moving for heap trees. Okay. Sir, how we are getting that means I will try to explain now. Okay. So, what is the general meaning of heap tree means? Heap tree is a specialized binary tree. Heap tree is a specialized binary tree and it follows two properties. It follows two properties. One is it has to be complete binary tree. Have you observed this terminology? What is complete binary tree? In complete binary tree, all the n-1 levels should be completely filled and the last element should be as left as possible. That's the meaning. Right? Heap tree is a kind of specialized binary tree and it has to follow complete binary tree properties and heapifying mechanism. Has to follow heapifying mechanism. If any tree follows these two properties, then we call it as heap tree. Right? First, what is the meaning of complete binary tree? Let's say 1, 2, 3, 4, 5, 7. Is it a complete binary tree? No, it is not complete binary tree, right? Because at the last level, the elements are not as left as possible, right? So, if I say something like this, is it a complete binary tree? Yes, this is what the meaning of complete binary tree, right? So, it has to be compulsory first complete binary tree and it has to follow the heapifying mechanism. What is the meaning of heapifying mechanism means? Heapifying mechanism means generally based on our requirement. In general, heap trees are of two types. One is max heap, another one is the min heap. In max heap, it follows the principle, it should be a complete binary tree. It should have to be a complete binary tree. So I can write it as CBT, complete binary tree. Along with complete binary tree, it has to follow a principle. The principle is something like the parent elements should be greater than or equal to its children. The parent values should be greater than or equal to its children. If you go with the min heap, it should be a complete binary tree where the parent values should be less than or equal to children. Just note on the definition. I will give the clear example. You will get the complete idea. Okay. For example, I am trying to draw an example 89. Let me give 88, 69, 35, 74, 62, 64, 20, 15 and 40. Observe this particular diagram. I have to classify whether it is max heap tree or not. Okay, fine. If I would like to say whether it is max heap or not, first what is the minimum criteria it has to satisfy? Complete binary tree. Can you say is it a complete binary tree? Yes or no? Yes, it is a complete binary tree because all the n-1 levels are completely filled and the last level is as left as possible. So I call it as complete binary tree. Then as I am saying that this is a kind of a max heap tree, what is the rule it has to follow? You have to identify its parents. What are parents here? 89, 88, 69, 35 and 70, which I can say that all the non-leaf nodes, am I right? All the non-leaf nodes are nothing but parents or not? Yes. All non-leaf nodes are nothing but parents. So try to select the first non-leaf node from the last. Does the 74 is a non-leaf node? Yes or no? Yes. Now is it following the, does parent is greater than or equal to children or not? Yes? Yes. This particular node is satisfying. Good. Then go to the next non-leaf node. What is the next non-leaf node? 35. Does 35 is greater than its children? 20 and 15. Yes. 35 is greater than or equal to 20 and 15. Good. Next 69. Is it greater than its children? Children means what? 62 and 64. That's it. Is 69 is greater or equal to 62 and 64? Yes. Then go for 88. Does 88 is greater than its children? Yes. So don't go for beyond it. Just go for next children. That's it. Don't go for sub children. Because once the children is satisfied, the next level also already satisfied. Because we are moving from what? From bottom to top only. So 88 is greater than 35 and 74. So it is satisfied. Next go for upwards. Does 89 is greater than 88 and 69? Yes. So as this complete tree satisfying parents are greater than or equal to its children, we can call it as max heap tree. We call it as max heap tree. Okay. So this is the meaning of max heap. So in the examination, they might provide, does the given tree is a max heap or not, they might ask. So you have to cross check it. How we are going to cross check? You have to start from the non-leaf node and you have to validate its properties. Fine. So let me give one more example. Let's say 10, 20, 50, 30, 80, 60 and 70. Is it a mini heap tree or not? Yes, it is mini heap tree. Why we are calling it as mini heap? First thing is it is a kind of complete binary tree and you have to start with a non-leaf node. What is the non-leaf node? 50. So you have to start from 50 onwards. I am just trying to define an algorithm also including 50. Does 50 is smaller than 60 and 70? Yes. 20 is smaller than 30 and 80? Yes. 10 is smaller than 20 and 50? Yes. We will stop the process and we can say that yes, it is a kind of mini heap tree. Good. So once you are able to understood the meaning of max heap and min heap, the next question is how to implement it. How to implement it? Once you have a tree, you have to identify whether tree is following the max heap property or not, or min heap property or not. You have to do. What is the first step generally you have to follow? You have to find out the non-leaf nodes. Where the non-leaf nodes, how we are going to identify? See, this is a kind of representation which is generally meant for us. Am I right or not? It is meant for us. What about the system? System is going to store in terms of what? In terms of an array. Am I right? So for example, if I try to draw the same structure, 89, 88, 69, okay, 35, 74, 62, 64, 20, 15 and 14, right? This is the max heap tree. max tree, right? This is for our representation. What about the system? System try to store either in the array representation or it will store in the form of a linked list representation. Am I right? If it is going to store in the form of array representation, is it going to store in the form of like level by level? So first 89, 88, 69, 35, 74, 62, 64, 20, 15 and 14. So whenever you have an array of data, what is the minimum criteria you have to check? You have to check whether is there any empty space or there or not. Is there an empty space or there? If there are empty space in the array, what is the meaning of it? Which is not a complete binary tree. It's not, right? That I have explained in the previous slides, right? So which is not a complete binary tree, right? If there are no space in the array, I can say that it is a complete binary tree. Am I right? It's completely filled as left as possible. Once we done, you have to find out what? You have to find out the non-leaf nodes. How we are going to find out the non-leaf nodes? Can you able to generalize? Let's say if the index starts with, assume that if the index starts with 1. If the index starts with 1, how will you able to find out the non-leaf nodes? Observe it. Here the non-leaf nodes are nothing but what? So I will try to draw some dotted notation for leaf nodes. These are all the leaf nodes, and the rest of them are all non-leaf nodes, right? Which means from 62 onwards, these are all the leaf nodes, and before 62 all are related to the leaf nodes. So from where you have to start traversing, you have to start traversing from the index position 5. This is where your leaf nodes, non-leaf nodes are going to be existed. So can I say that it will be from 1 to 5? It will be 1 to 5. So that I can able to derive it as 1 to floor of n by 2. 1 to floor of n by 2 represents the non-leaf nodes. Observe, what is the value of n here? 10. Total number of nodes are how many? 10. 10 by 2 is what? 5. Which means, is it 1 to 5 or non-leaf nodes or not? Yes. You can take now 5th index position and try to get its value. 74. And once you know a particular element, from this can you able to get its left child? Yes or no? I have given already a formula. 2i. 2i means what? 2 into index position is 5. 10. So go to the index position 10 and get the value. Does 74 is greater than 14? Yes, condition is true. And you have to check with the right side condition also. But if it goes here, it is beyond. So we will just simply skip it. Next we will start with, yes, here it is satisfied, right? Here it is satisfied. Next go for index number 4. I will try to decrement the next non-leaf node. Index number 4, 35. Does 35 is greater than 2i? 2 4s are 8, right? 2i, 20. Yes, satisfied. Does 35 is greater than 15? Yes, we will move on. Right? So like this, we will try to move on. Right? Once the complete all the conditions are satisfied, I can say that it's a kind of max heap tree. The same procedure we are going to move with the mini heap tree also. Okay. Observe, for example, so you might get question, right? Where you are getting the time complexity of big O of log n, right? So for example, we have a max heap tree. Let's say they are saying that there is a max heap tree. There is a max heap tree with set of values 40, 30, 20, 10, 15, 16, 17, 8 and 4. They are saying that this is a max heap tree. Okay. Now you need to insert 35. You need to insert 35. Right? I already mentioned that inserting a data requires how much time? big O of log n. Okay, good. Right? Can I prove it that? Try to construct the tree for this. They are saying that it is a kind of max-heap tree. 40, 30, 20, 10, 15, 16, 17, 8 and 4. It's a max-heap tree. Yes, means that the data is already in order. Right, as per the order. Now, if somebody asking for us to insert the new node, where you will insert? You will insert the last node of the array. You will insert the last part of the array. So, whenever I am going to insert at the last part of the array, this 35. Now, inserting this 35 is going to make the tree as invalid max-heap tree. Invalid max-heap tree. Then what you have to do? You have to make it validate. You have to make it valid max-heap tree. Then, can you do that? Can you able to find out its parent? Can you find out its parent? How will you find out its parent? If you observe, for every node, we have two children exactly. We are trying to discuss complete bind, right? Exactly, definitely, it is having two children. So, the parent you can able to get. It with the I by 2. The parent node of a node. You can get it with the I by 2. Right? If this is the node where I have inserted in the array, you should have to compare with the array. Right? What is the node number here? So total 3, 4, 7, 10. This is the index position 10. What is the parent of this one? 10 by 2, fifth index position. What is fifth index position? 1, 2, 3, 4, 5. Are you getting or not? Yes. Now the parent node value is greater than the corresponding inserted node. Is it true? Condition fail. When the condition fail, what you have to do? You have to swap them. 15 and it should be 35. It should be 15. And you have to repeat the process continuously until what? Until the condition is fail or until you reach to the root node. So now 35 is going to compare with the next parent. How will you get the next parent? 5 by 2. What is 5 by 2? 2. So I will try to compare here. So 35 and it will be, let me try to write it. So this will be 35 and here it will be 30. Now I will try to compare the next parent. What is the next parent? 2 by 2, which is 1. Does 40 is greater than 35? Yes. So we will stop the process. If you observe, I am adding an element at the last. And I am trying to move my element towards subdirection. And every time I am trying to minimum skip half of the elements. I am skipping half the elements. So this is the reason insertion is going to take a time complexity of big O of log. Right, here the scenarios will be very, very different. I am just saying for inserting an element. For inserting an element, it is going to take time complexity of big O of log n. Okay. For deletion also, it is going to take a time complexity of big O of log n. But for constructing the heap, I can say for building the heap, again it is going to get a time complexity of big O of n. Okay. So, but why just we have introduced the concept of heap trees means only for insertion. If your database contains frequent number of insertions and frequent number of deletions, then the heap tree is the better choice. If our database contains searching operation, if your database contains frequent search operation, then sorted array is the better choice. Right? Based on the requirement, you have to move. Okay. Fine. This is about the max heap or min heap tree. Is it clear for everyone? Right? Fine. So now what you can do now? Try to construct a max heap for the given data. So for example, construct max heap for 20, 10, 15, 7, 4, 18, 28, 23, 12, 14, 17, 25. This is the question they have given, right? What is the first step you have to follow? So you have to go with the step sum. You have to construct the maximum. Now generally, you have to first construct the heap tree. Construct heap tree. What is the meaning of heap tree? By default, it follows the complete binary tree property. It follows the complete binary tree property. So, whatever data you are having, you just simply place in the form of complete binary tree. 20, 10, 15, 7, 4, 18, 28, 23, 12, 14, 17, 25. That's it. This is the first step you have to do. So, in the previous slide I mentioned, constructing a heap requires big O of n time. This is what the meaning. Constructing a heap requires big O of n time. Once you constructed, then you have to go for validating the tree. Validating, or I can say as heapifying the tree. Why you are making the heapifying the tree? Because to get the output as a max heap or to get the output as min heap. So from where you start the process? Start from, very good, you should have to make it, start from non-leaf node. You are going to start from the non-leaf node. How we are going to find out the non-leaf node? Non-leaf node. 1 to n by 2. 1 to n by 2. So, if I say 1 to n by 2, you can start from 18. You can start from 18. Right now, I wish to go for constructing what? Max heap. Max heap. Does 18 is greater than 25? Condition fail. Right? So, means which is violating parents are greater than children. So, max heap means generally parents are greater than or equal to its children. So, what you can do now, you just simply replace this value with 28 or 25? 25 and this will be 18. Done. Right? We started from the non-leaf node. And we have to repeat the process until what? Until you have to reach to the node number 1. Node number 1. So, next we will try to go for next node. What is the next node? Node number 4. Node number 4. Is it satisfying the children's property? No. 4 is greater than or equal to 14 and 17? No. So, take out the largest value. What is the largest value? 17. Largest value 17 and replace with which value? Smallest value. Smallest value 4. Okay. Done. Next, move with the next one. 7. Does 7 is greater than or equal to children? No. You have to replace it with the largest value 23 and 7. And 7. Okay. Next, go with the next non-leaf node 15. Does 15 is greater than or equal to 25 and 28? No. So, it will be 28 and here it will be 15. 15. Okay. Next, go with the next non-leaf node. Next non-leaf node is 10. 10 you are going to replace with which value? 23. Very good. So, here it will be 10. So, finally, we will move with the next step. 20 is greater than 23 and 28. So, here it will be 28. This will be 20, right? So, if you observe clearly, the output will be something like this: 28, 23, 20, 10, very good, 25, 15, 7, 12, 14, 4, 18. Somewhere we miss some logic, right? I made it intentional. What is happening here? What you observed? Once you move to one level up, you have to get back again. You have to get back to the next location until it is going to satisfy the thing, right? So where we did that? Observe it clearly. If you want, I can do it again. Twenty, 10, 15, 7, 4, 18, 28, 23, 12, 14, 17, 25. So you are going to start from the non-leaf node. Non-leaf node is 18. So you are going to compare. Does 18 is greater than 25? Condition fail. When it is fail, you have to swap it. You have to swap it. Once you swap it, what you have to do? You have to again compare with its children. You have to compare with children. So here there are no children. We will stop the process. Then take out the next non-leaf node. So here you will get 17 replaced with 4 to make it max property satisfied. As there are no children, I will stop the process. I will move to the next non-leaf node. Next non-leaf node is 7. Does 7 is greater than 23 and 12? No. I will swap it with the largest value. So 7 will here 23. And 7 again I have to swap it with, again I have to compare with the next leaf node. Is there any next leaf nodes are there? No. We will stop the process. Now we will move to the next non-leaf node. 15. Does 15 is greater than 25 and 28? No. Then I will swap it 28 and it will be 15 number. Very good. Okay. Now 15 has to compare again with the next level. Is there next elements are there? No. We will stop the process. Good. Next, go with the non-leaf node 10. Right? 10 is greater than 23 and 27? 17? No. So I will go for here 23 and I will try to write here 10. Here. Now swapping done. When swapping done, what you have to do? You have to compare with children. Right? 10 is greater than 7 and 12? No. So you have to reiterate the process. So here you have to get 12. It will be 10. Okay. Now 10 is at the leaf level, so we can stop the process here. So next, we'll go with the next root node 20. Does 20 is greater than 23 and 28? No. So we have to swap with the largest element. Here 20, it will be 28. 20 is greater than the children? No. You have to go with the 25 and 20. Does 20 is greater than 18? Yes. We can stop the process. Right? So finally, if you observe, the output will be 28, 23, 25, 12, 17, 20, 15, 7, 10, 14, 4 and 18. Right? Now, is it a max-heap tree? Yes, this is the max-heap tree. So, in the exam, you have to write in the step-by-step process. You should not go for directly writing like this, cancellation and all the things. Okay, for the gate examination, finally they required answer. Which of the following tree is the max-heap tree? Or which of the following arrays satisfy the given data after inserting a particular node? Like that they will ask, you have to answer it. Fine, observe. Now, for this tree, what is the array? Can I write it clearly? 28, 23, 25, 12, 17, 20, 15, 7, 10, 14, 4, 8. Right? So the same thing we can represent in the array. This is also kind of max-heap tree. Max-heap tree. Now I will try to write some other one. Observe. 1, 2, 3, 4, 5, 6, 7. Is it what tree? Is it a max heap tree or min heap tree? It is not at all a complete binary tree. So we can't say that it is a max heap or min heap tree, right? For example, I mentioned something like this, 8. Now is it a max heap tree? Is it a min heap tree? Good, right? If you are able to say that it's a min heap tree, yes, definitely it's a min heap tree. If you observe something like this, important for the COMT examination, again this bit 9, 8, 7, 6, 5. I mean in a sorted order, either ascending order or descending order, this will definitely max heap tree. In the array, if you are able to observe ascending order, ascending order of data, definitely it leads to min heap tree. If you are able to observe some descending order of data, definitely it is going to be a max heap tree. But the question is it always compulsory that the data should be in descending order to get the max heap tree? No, right? If you observe here, is it always the data is in descending order? No, that's not the compulsory rule. But if it follows either a descending order or ascending order, it definitely fall under heap tree property. That you have to observe. Okay. Fine. So, can you able to tell me again? Can you tell me this order? Can you note down someone? Okay. So what is that order? 28, 23. Okay. 25, 12, 17, 20, 15. Good. That's it. Yes, good, right? So I will try to draw the structure again. 28, 23, 25, 12, 17, 20, 15, 7, 10, 14, 4 and 18 and 18. I mean, see guys, here they are asking for us to construct a max heap tree, right? Similarly, if they are asking us to construct a min heap tree, can you able to do it or not? Yes, we can able to do that. Fine. If you observe here, it is following the max heap property, so we can say that it is a max heap tree. Fine. Now, once you have the data something like this, can I able to get the maximum value? If I am saying that it's a kind of max heap, can I able to get maximum value? How will I able to get the maximum value? How much it will take? Big O of 1, because the maximum value is always placed at the top location. If somebody asking us to delete the maximum value, then how much time completion is going to take? Big O of n or big O of log n or big O of 1? We started the discussion on this concept only, right? When somebody asking for us to delete maximum value, deleting this value is nothing but what? Completely removing it. So that we need to adjust the entire tree, right? Of some levels, right? So it will lead to big O of log n. So for example, what you will do now? You will try to delete max value. Try to delete the maximum value. When you try to delete the maximum value, what you are going to get? 23, 25, 12, 17, 20, 15, 7, 10, 14, 4. Okay. Actually it is 18 and here it will be 28, right? So what I am saying, try to delete the max value. Try to delete the max value. When you are trying to delete the max value, to reduce the time complexity of arranging all the things, what you can do now, try to swap it with the last element. Try to swap it with the last element. I mean, you are going to simply delete the 28 and try to place 18. Place the 18 here. And then apply the heaping process. Applying the heaping process, right? After deleting the max value 28, what I am saying is remove 28 and replace it with 18. And instead of completely removing it, place it in the last position. Place it in the last position. Okay, fine. So it is performing how much time complexity? Big O of log n. Right? It has to heapify, right? Now observe what you have to do. After doing this process, this 18 has to compare with what? Next level elements. Is it a max heap? Is it a max heap? No. So you have to swap this particular 18 with which element? You have to replace this one with 25 because the largest value is. And once the modification is done, what you have to do? Again compare with the 18 and 20. So here it will be 18 and it will be 20. Now is it a max heap? Yes or no? Yes. It's a max heap. 25, 23, 20, 12, 17, 18, 15, 7, 10, 14, 4. What about 28? You have to skip it. You have to remove, like you have to say that 28 is removed. 28 is removed, that's it. Okay. So which means that once the swapping is done, once the removing the maximum element, you can consider that you can reduce the size of the array. You can reduce the size of the array. For the next process, try to delete the maximum value again. So what will happen to this array? Is it completely modified or not? If it is completely modified, which will be 25, 23, 20, 12, 17, 18, 15, 10, 14, 4, and this data will be assumed as is. See, I am trying to build certain logic actually here. Now observe. When again try to delete the maximum value. Try to delete the maximum value. What is the maximum value? 25, right? Delete it. What do you have to do? Replacing it with the which value? Last element. What is the last element? We already reduced the size. So which is 4. You have to swap it. You have to swap these two. Okay. So when we are going to swap it, what will happen? The array will look like something like 4, 23, 20, 12, 17, 18, 15, 7, 10, 14, 25 and 28. Observe. I am going to skip the, I have reduced the again array size, which is 25 and 28. So what will happen? Once we did it, 4 will be available here. Am I right? So again you have to heapify it. So let me write it. So if I draw the diagram for this, how the look like is 4, 23, 20, 12, 17, 18, 15, 7, 10, 14, that's it. This is the way you are looking like, right? Now what you have to do? Once the swapping is done, you have to heapify it. So 4 will be here, 23, and 4 replaced with 17. This will be 14 and it will be 4. Which means what I am doing here, every time I am trying to delete maximum value. Every time I am trying to delete the maximum value. At the end, what you are getting? Can you expect the output? What is the output? 4. This process is continuing. 4, 7, 10, 12, 14, very good, 17, 18, 20, very good. This is the data you are going to get. So what is the output you are expecting? Some kind of order. So you got some sorted data. So you got the sorted data, right? The mechanism what you applied here is heap sort. So what is heap sort? What is heap sort? So trying to take out the last element of the node and place in the first portion, applying the heapifying process. And this process is going to be repeated completely. You will get the finally sorted data. This mechanism what we call it as heap sort. Okay. So simple. In heap sort, the steps is replace last element with first element. We are not going to do any kind of comparison, something, all the things, right? And we are going to reduce the size. We are going to reduce the size of array. And after reducing the size of the array, what you are going to do? You are performing heapifying from first position. Heapifying from first position. And this process is going to be completely repeated. So I can say repeat 1, 2, 3. Right? If you repeat the process 1, 2, 3, you will get finally sorted data. Okay, now. So if you do this process, so what is the time complex you are going to get? So for heap sort, time complexity, can you guess it? For deleting one max value and trying to do the process, you are getting how much time complexity? Big O of log n. Okay. For making n elements, how much time complexity? Big O of n log n. That's it, right? For heap sort, the time complexity will be big O of n log n, right? And if you look into the some properties, the properties of heap sort. So earlier I used to discuss various kind of properties regarding the sorting techniques, right? So similarly, heap sort is not stable algorithm. I hope you remember what is the meaning of not stable algorithm, which means the order in which you are getting the duplicate values, the order might change in the output. Okay, so that's what the meaning of not stable, and which is an in place algorithm. Heap sort is a kind of in place algorithm. Okay, and the important point is heap sort is better than quicksort in worst case. So when the quicksort behaves the worst case, very good. So time complexity big O of n square. For sorted data, quicksort behaves the big O of n square, right? Heap sort, even for the sorted data, it will get a time complexity of big O of n log. That's where heap sort is better when you are going to compare with quicksort. Fine. So we can stop here, Amma.